Hi, Enthusiastic Steve here, and Happy New Year to those I've not spoken to before, and all the very best, and hope everybody's staying safe wherever they are. Now, today's video, it's kind of a little experiment really. I'm going to try and attempt to build a 2-element beam antenna, a simple Yagi, but I'm going to be using garden bamboo canes, simple bamboo canes. Not aluminium, and I'm going to put wires down these bamboo canes to actually make this 2-element beam. The idea is for a beam to work on 10-meter band and the 11-meter band, and we'll see how we get on. Now, as you know, I'm not new to experimenting with antennas. For those of you who remember or recall, do you remember watching the previous video I've done on an aluminium ladder? Where I used two parts of an aluminium ladder connected to a coax as a simple form of a dipole, and I used the propagation mode tool Whisper, and I was getting reports back from the USA, from here in the UK. That worked fantastic, and I've always wanted to play with a beam antenna, but my garden's not really that big. It doesn't really fit a beam antenna, so I've only ever really played with quarter waves and 5/8 wave antennas till now. But construction wise, electrically it's very simple. There's a few basic concepts you need to get into your head, but once you've got those, you can scale this design up or down to fit any band you want. So, and it can be of different materials. I'm using bamboo canes, just one because it's cheap. I've got them around the garden, and it just proves if you want to experiment with a beam antenna, anybody can do it. If you want to make this out of aluminium later, just scale it up or scale it down, get the appropriate aluminium poles and bars and make one for a more permanent structure. But where I go, this is just purely experimentation to prove the concept that you can make your own 2-element beam antenna. So there are two parts to this really. One, the electrical design, which I'll go over on paper in a minute, and then two, the mechanical, the engineering bit, to be able to get this constructed so it holds itself together as designed. So let's have a look at the paper, let's have a look at the electrical side of it, and I'll go through a few basics and blow out some myths about these beam antennas. So what are we going to try and achieve today? Well, we're going to build a 2-element Yagi antenna. This antenna is going to be resonant on the 10 and 11 meter bands. So let's take a quick look at the design of this antenna. It's very simple. It consists of basically just a dipole fed by a coax, 50 ohms, with a reflector behind that. Simple, isn't it? That's all it is, a dipole with a reflector. All we need to work out is the sizes of the dipole, the size of the reflector, and the distance between the reflector and the dipole element. So let's take a look at the actual dipole element itself, the simplest part of the antenna really. All it is, a dipole is two wires, both cut to quarter wave, and then the feed point is actually in the centre. So in this case we are going to feed this antenna with 50 ohm coax cable. So I've got a little dipole centre which I'm going to actually connect in the middle with the actual little connectors on there, and the coax cable will go into the base. Just for ease, you could just solder the wire or coax directly to the legs. It doesn't make no difference. Now, a quarter wave on this frequency, okay, the band I'm looking for is the spread between the 10 and 11 meter bands. I'll be starting from approximately 27 megahertz, and the design's got to go up to about approximately 28.6 or 7 megahertz. So in the center, we're going to call it 27.6. Okay, that will suffice and cover both the 11 meter UK and European frequencies and the bottom end of 10 meters. If I need any more, a tuner on the radio or a manual tuner will give you an extra bandwidth on top of that. So I'm aiming for 27.6 megs. So use an online calculator or do a simple calculation to get the length of wire, and we're looking for half wave of that frequency. You divide it by 2 to give you your individual quarter wave legs, And in this instance, it turns out to be approximately 2.58 metres, or in old school money, 8 foot 6 inches, give or take a hair or two. So, and again, it depends on the material you'll be using. If you're going to make a more permanent structure using aluminium rods, or you just got whatever you got laying around the house, just bare wire or wire and insulation, you must take into account that some of these have velocity factors of the actual speed the RF travels through the wire due to resistances. So they might not be exactly 2.58. You may sometimes have to just lengthen a tad or just shorten them slightly. This is a good starting point, and you won't be far off if you construct it at these lengths. You can scale this up for, as long as it's quarter wave legs, for any frequency. So you can go any bands from 80, 160, 80, 40, 20, you name it, all the bands up, even 4 meters, 2 meters and 77s. You can use the same design, just scale it up or down as required. So to make this into a form of Yagi, or 2-element antenna, we need to reflect back some of that energy from our dipole into a certain direction. And we achieve this by adding a second element behind the driven element. Now this is just a conductive wire, or the rod of aluminium, depending on how you're making it. It's continuous. It has to be, this is the important part, or one of the important factors, has to be at least 5% longer. Okay, so that's 5% wider than the actual dipole itself. No limit, you can have it 10% wider if you need, but as long as it's at least 5% wider, it will act as a reflector from your driven element. The next important rule we have to apply is this here. I've drawn the arrow in already. It's the distance between the driven element and the reflector. Now, I've always led to believe that it always is quarter wave. Well, technically, yes, partly true. It can be up to a quarter a wave apart. But I was led to believe it was always a quarter wave. This is not true. It's a bit of a myth. You can have this element up to as close to that dipole as 0.18 of a wavelength away. But there is an optimum. The optimum distance is 0.16 away. And you have to do a little bit of a calculation. You have to work out the wavelength. There's different ways of doing it. I just calculated the wavelength, divided it by 100, and then times that by 16. And that gave me 0.16 of a wavelength away. So I did some calculations, and I wanted it 0.16 of a wavelength away from the actual driven element, which in this case is approximately 5 foot 4 inches. Okay, or I think it's 1.64 meters. You could hear the old brain there, the old cobwebs there slowing down a little bit. 1.64 was the actual answer. So why is this important? Well, how can it be so close, or can it be up to quarter wave? What does that affect? Well, it affects a couple of things. You can increase the gain by actually having the reflector closer to the dipole, but the bandwidth dramatically decreases. If you move the reflector back to quarter wave behind the driven element, the gain reduces, but you get a larger bandwidth. The optimum is somewhere in the middle, as far as this is concerned, is at 1.64 meters, 0.16 of a wavelength behind it, because this gives you a good match at 50 ohms. So this gives you the best VSWR. You lose a little bit of gain and you get a decent bandwidth. Okay, depending on what you're trying to aim for. So I've gone for a little bit of a compromise, aiming purely to get a good VSWR and a good match on the antenna to make it as resonant, as efficient as possible. So that's the electrical principle of a beam antenna. Okay, you can apply that to any beam design. So the next stage is, let's take a look at the actual construction. So first of all, for construction, use an online antenna app to get the actual dimensions of the antenna. I decided for ease of use to use a centre dipole connector. So I cut some wires to the quarter wavelength, added some crimps, and then connected those to the centre dipole connector. I then used some insulating tape to protect these connectors. This is a simple experiment, so just some basic tools and some bamboo canes from around the garden. Add to this an assortment of tie wraps and I was ready to go. Join some bamboo canes together to give you the desired length for the dipole. Attach the tie wraps around them to secure, and then lay the wires along the length of the bamboo. Repeat this process to make the reflector. For the main support arm, I cheekily used the downpipe of my old shed. Measured out the distance between the pipe for the reflector and the dipole, drilled some holes, and then passed the bamboo canes through them, secured with tie wraps. Definitely not the tidiest of installations, but more functional, it works. So there we have it, the experimental 2-element Yagi antenna, made out of bamboo canes. Pandas not included. Now we can see it, I've got it on a base of a DX commander pole, and it's sitting there very comfortably indeed. All we need now is some DX skip to test it out either on 10 or 11 meters. But at the moment, unfortunately, the bands are very quiet. But let's go and check the VSWR. Right, we've just stepped back inside to the Radio Shack now. I've connected the antenna up to my little shortwave linker, and we're going to transmit on the middle of the 11 meter band, and then we'll go up into the 10 meter band and go back down to the bottom of the 11 meter band, see how the VSWR is. Right, here is the view of my VSWR meter, my little trusty manual Comet tuner. We're transmitting on low power on FM, and they're going to be on the top end of the European 11 meter band, which is about 27.405 megahertz. So here we go, low power, just under 5 watts, and it's just moving the needle. It's under 1 to 1 it's 1 to 1 VSWR there. So happy with that. So on the bottom end of the European 11 meter band, we'll try there. Very little difference in VSWR, still very low. In the middle of the UK channels, and let's press the button and see what we get. A slight difference, but it's a 1 to 1.2, so perfectly reasonable. And again, if I wanted to tune that out, I could. And now we're up to the 28.6. Expected a little bit higher VSWR. And there we go. We're probably about 1.6, 1.7 there on the meter. Again, it's usable. There's no problem with that at all. And with a tuner, we can just bring that right down to 1.1. So VSWR, very happy. I could go back to the antenna. I could just tweak the driven element slightly. But for experimental purposes and proof of concept, the 2-element bamboo antenna works. Just got to wait for some skip now. As there's no skip, I tried it on Whisper propagation tool and got down to French Guiana, South America, nearly 7,000 kilometers away. So the antenna does work, and it's only 8 foot off the ground. Well, hopefully that's encouraged some of you maybe to want to go out and try and build your own 2-element antenna. The advantages of these are pretty good gain. The largest gain from a dipole antenna comes from fitting a reflector. You can get up to 4 dB of gain. Adding further elements in front of the dipole to actually narrow down the beam width actually only gives you between 1 and 2 dB gain per an element. This has been Enthusiastic Steve making these little 2-element bamboo antenna. So all the very best, and 73s.